we're going to start off by looking at 7.5, part 1. And when we talk about special angles, like I asked you to find angles on a unit circle, does anybody remember what multiples all those angles had to be? They were multiples of one of two numbers. Yeah, huh?
30 or 45.
Right, they were all multiples of 30 and 45. So if you look at the unit circle and you map out all the multiples of 30 and 45, you get 45, and then you get 30, which is 15 away from it, and you get 60, which is also 15 degrees away from 45. So if you do that in all the quadrants, you kind of get these 3 points that are centered in the middle of each quadrant. But it looks like we're kind of missing something. We have gaps kind of at the beginning and at the end. And this is a gap for the 15 and the 75. These are angles that we've never done. But if you fill those in, now it looks like we have equally spaced points all around the circle, every 15 degrees. So what we're going to look at is how can you find trig functions of angles that are multiples of 15, like 105, 75, things like that. And we're going to use what's called the sum and difference identities. So to figure out angles that are multiples of 15, any of those red ones, this would be like 15, 75, 105, this would be 165, things like that. You have to know the other ones as well. All right, so it's probably a good idea just to go over some decimals that you're going to see, because if you don't remember how to do it exactly on the unit circle, you can kind of get away with recognizing the decimal and seeing what that would be as a fraction with a square root. So some numbers that will pop up. 0.707. Does anybody remember what that is as a fraction, and it involves a square root? So how about in the 45, 45, 90 right triangle? Does anyone remember the lengths of the sides? And this one was 1. Yeah?
Square root of 2 over 2.
Square root of 2 over 2, and that is 0.707. So if you have the triangle memorized, you can figure it out every time. But if you don't, when we get to a problem, you can look at the decimal, and if you see something with a 0.707, well, the square root of 2 over 2 is approximately 0.707. Okay, another one that you're going to see, let's see, is 0.577. That's a decimal that pops up. Let's do this one first. 0.866. 0.866 is a decimal that comes up in the 30, 60, 90. This was your 45, 45, 90. Does anyone remember what the sides are in the 30, 60, 90? Yeah?
So 1, 2, square root of 3?
So if the hypotenuse was square root of 3, yes. But does anyone remember what they were on a unit circle, if the hypotenuse is a 1? How about the side opposite the 30? That was a nice number. It didn't have a square root in it. Yeah?
1.
Well, the hypotenuse is 1, so it has to be smaller than that. How about, does anyone remember the other square root that was involved when you do the 30, 60, 90 right triangle? Square root of 2 is involved with the 45, 45, 90. But square root of, yeah?
Square root of 3 over 2.
Yeah, square root of 3 is involved here. So this is how we label the 30, 60, 90. And the square root of 3 over 2 is the number 0.866. So if we see a 0.866 in a problem, we can rewrite it as the square root of 3 over 2. So those are the main ones that we're going to use. This is the only two numbers that would come up when we're dealing with sines and cosines. Well, I guess you could have negative 0.707, but you just put a negative in front of that. When we get to tangents, if there's any special numbers you need, we'll take a look at that. Okay, those are the two we'll need for now. So let's take a look at this. So I want you to look at the sine of x plus 3 compared to the sine of x plus the sine of 3. And what I want to know, does anyone think that those two things are the same? Or do you think they're different? What do you think? Yeah?
I think they're the same thing.
You think they're the same thing?
Actually, no, I don't think they're the same thing.
You don't think they're the same thing?
Right.
Okay, why?
Well, because there's the sine of x plus 3 is a value, but if you just have the sine, well, maybe. Actually, I don't know. I'm not sure. Let me check.
Yeah?
I think they're the same because it's just distributive property.
Okay, so I guess that would be kind of the question. Can you distribute sine? Let's think of it from a transformation perspective. What's happening to the sine of x function here? What's the plus 3 doing to the one on the left? So
Left 3.
it's moving it,
No, left 3.
wait, let me think for a second. Plus, yeah, it's going to move it left 3. Yeah. So it's moving it left 3. What's happening with the one on the right? What kind of transformation do we have there? Nick?
Vertical stretch or vertical compressive 3?
No, there's no stretch or compression there. Stretching and compressing involves multiplying. So there's no stretch or compression. Yep.
Is it moving it up by sine 3?
Yeah, that's a vertical shift up by the sine of 3, whatever that number would be. So the one on the left, this is a shift 3 units to the left. This is a shift up by the sine of 3. That's not the same thing. All right, if you just think about it from a transformation perspective, they're different transformations. So they're not the same. So the distributive property, you can't do that. So what we want to know then is, well, what can you do? If you have a sum inside here, how can you rewrite it so that it's not a sum? So you can kind of separate it out so you just have like one single variable for your argument and not something with a variable plus a number. Okay, how do we do it? So let's take a look. So we're going to start with these four main formulas we're going to look at today. All of these formulas are going to involve a sum or a difference. The first one we're going to look at is a difference formula, and it has to do with the cosine function. Now we can prove this one. It's a little hard to prove it, so we're not going to go through the proof of this formula. But when we do another one, like when we get to the cosine of a sum, then we'll prove it based on this one. All right? So we will eventually get to this. This is what we call sine of a sum. How do you deal with the sine of a sum? But we're not there yet. We're going to start with the cosine of a difference. And that's the formula that you use for cosine of a difference. Again, the proof is in your book. The thing is, it'd probably take about 20 minutes, maybe 15 minutes to go through exactly where that comes from. So the value of going through that for 15 minutes versus actually getting to more material that's going to be helpful, the proof is just, it is kind of lengthy. Okay, so cosine of a difference. You're going to have two angles inside your argument. One angle minus the other one. And there's some patterns here we can look for that'll help us to kind of remember the formula. Whenever you have a cosine formula, whether it's the cosine difference or the cosine sum. We haven't done the sum yet. When you break this up, it breaks up into 4 trig functions. 2 cosines and 2 sines. The cosines are together and the sines are together. So when you have the cosine formula, the cosines stay together when you break it up and the sines stay together. And the symbol you put here is the opposite of the one you had here. Sometimes it's the same, sometimes it's the opposite. In this formula, it's the opposite. And the way that I usually read this is cosine of the first times cosine of the second plus sine of the first, sine of the second. And when I say first and second, I'm referring to my first angle and my second angle. Any question on the formula?
Never.
Again, proof, it is on page 409, but it's a little lengthy. It involves drawing some diagrams and measuring angles. We're not going to go through it, but that's what it involves. All right, so let's see if we can use that formula to figure this out. The whole goal, if you're doing something numeric, is when you write this as a difference, which is the only way we know how to break something up right now. We haven't learned sum yet. But when you write something as a difference, the 2 angles that you put here and here need to be multiples of 30 and 45. So you have to figure out a way to write 15 using numbers that are multiples of 40, 45, and 30. If we pick angles that are not multiples of 30 and 45, you're not going to be able to figure out the exact answer. So can anybody think of the simplest way to write the number 15 as a difference, and I need 2 numbers that are multiples of 30 and 45? Okay?
45 minus 30.
Yep, 45 minus 30. Now, when I refer to my first angle, when I split this up using the formula, it's a 45. And when I refer to my second angle, it's a 30. This is the first angle. This is the second angle. That's your alpha. That's your beta. So now, take those 2 numbers and fill them in everywhere you see alpha and beta. So it's cosine, cosine, plus sine, sine. So we're going to have cosine, cosine, put the opposite of the minus sign, and then sine, sine. And now what goes in for the arguments is first, second, first, second. So we've got 45, 30, 45, 30. And now every one of those trig functions is a problem we could do with unit circle trig. This is four values we need to figure out. If you have to go back to the unit circle every time, it's going to take a while. That's why if you can recognize the decimal equivalent, then that's going to be a lot faster. So let's start with cosine and make sure you are in degrees. All right, cosine 45. I do not want to write 0.707. That's rounding. What is 0.707 as an exact answer? Yep.
Square root of 2 over 2.
Yeah, and you can check if you're not sure. You can just type it in, square root of 2 over 2. But that's what it is. Okay? And that's figured out using unit circle trig. So 0.707 times. Now we're going to do the cosine of 30. And that comes out to 0.866, and it keeps going. What's 0.866 as a decimal? Yeah, as an exact answer.
Square root of 3 over 2.
Yeah, and I'll check it. This will be the last one I check because then we'll have checked both of them. So square root of 3 over 2. plus sine of 45. And that's going to give me what for the sine of 45? Square root of 2 over 2. And the sine of 30, that's going to give me 1/2. So just 1 over 2. All right, so now just simplify, clean that up, and that's our answer. Okay. What do I get when I multiply these two together? Yep.
Square root of 6 over 4.
Yep. Square root of 6 over 4. And what do I get when I multiply these two together? Maybe?
Square root of 2 over 4.
Square root of 2 over 4. Now, since they both have a common denominator, we could just put that together as 1. Might as well do that. Square root of 6 plus square root of 2 over 4. And that is the final answer. Now, very easy to check it. Let's type in cosine of 15, see what we get. And then let's type in what we just got in that box and see if they come out the same. So cosine of 15, 0.9659. And let's type in square root of 6 plus square root of 2 over 4. Square root of 6. I should have done parentheses. If I don't do parentheses around the entire numerator, the divide by 4 part, it's not going to work right. Okay, so put that here, hit divide by 4. And if you look, we got exactly the same. So that's how you can find the exact answer of cosine of 15. Any questions on that? Okay, it's good to know how to do something numeric. That's not really the real strength of these identities, doing things with numbers. Verifying and proving identities is more where these come in handy. But you can do things with arithmetic and numbers like we just did. Now, you know the exact answer for the cosine of 15. So now, let's say you had to split up something. Like here, you were trying to find two numbers that subtract to give you something else. Technically, you could now use 15 as one of these numbers. But the problem with that is you'd have to remember this answer. All right, so we generally don't go back to using like a 15 in here or a 15 over here because it's hard to remember what that answer is. Okay. We generally stick to the 30s and 45s. Okay. Questions on that? All right, so that's the exact answer for cosine of 15. Now, let's do something that's much more kind of significant, and that's actually using the identities to prove something. The nice thing about proving something with a sum or difference identity, compared to the ones you did last week, you don't really have many paths you can choose here. You really only have one thing you can do. So remember, when we want to prove an identity, or verify an identity, does anyone remember which side I said to always start with? Yeah?
The harder side.
Yeah, always start with the harder side, because there's more stuff there to work with that you can simplify. Don't try to take something simple and complicate it to look like the other side. Always take what's more complicated and try to simplify it. So we're going to work with the left-hand side. Now, on the left-hand side, which trig function am I using?
Cosine.
Cosine. And what operation is inside the parentheses in my argument? Yeah,
Subtraction.
subtraction. So this is a cosine of a difference. So what you want to do now is look up your cosine difference formula and then fill in what you can. Right? And then we'll see what happens. So cosine of a difference. How does that, can someone remind me, how does that one start out again? Yeah?
Cosine of the first angle times cosine of your second angle.
All right, so I'm gonna have a cosine, cosine. What comes after that? Cosine, cosine, and then, yep.
Sine.
Before that.
A plus sign.
A plus with this identity, what you put here is always the opposite of what you had there. That's always true for the cosine identities. Cosine sum or difference. Okay, so this is the difference. All right, so we got that equals, and what's going to come after the sum? Tim?
So I have square root over 2 instead of negative theta.
Yeah, so we're going to have sine, sine. And now I'm going to fill in all my arguments. So I generally like to write the formula first, so I don't have to think about what the formula is and plug into it at the same time, because some of these formulas start to get a little more complicated. All right, so we got cosine, cosine, plus sine, sine, pi over 2, theta, pi over 2, theta. Now the thetas you can't do anything with. Those are just going to stay where they are, but we can evaluate the cosine pi over 2 and the sine pi over 2. Now, pi over 2, what angle is that? John?
90.
90. That's a quadrantal angle. Anytime you take sines or cosines of quadrantal angles, the answers you always get are 1, -1, and 0. So this is going to come out to a very nice number. Can somebody tell me what the cosine of, if you're doing it in degrees, 90? Or if you're doing it in radians, what's the cosine of pi over 2? Or even think about it on the unit circle. What's the formula for cosine on the unit circle? Once you know the coordinate, it's the what value? Tim?
45 degrees.
Well, it's once you know the coordinate, what part of the coordinate is your cosine? Want to remember? Tangent is y over x. But what's cosine? John?
Yeah, that's x over 1.
That's cotangent. When you flip the tangent.
Oh, is it 1 over x?
1 over x would be the secant. So,
X over 1.
yeah, just x over 1, just x. So cosine is your x value. Think about 90 degrees on the unit circle. What's the x value of that coordinate? 0. Okay, so if you don't have a calculator, that's one you can figure out reasonably quick. Just knowing it's the x value, and the x value of 90 is 0. So that's 0 times cosine plus, now we're dealing with the same point again, but with sine, what part of the coordinate are you interested in? The y. And what's the y value when you're at an angle of pi over 2? 1. So 1 times sine. What's going to happen here? Yeah?
I'm going to be left with sine theta.
Yeah, because 0 times cosine, this cancels out. So all I have is 0. 1 times sine is sine. And 0 plus sine, well, that's just sine. And that is exactly what they wanted us to get. Any questions on that? Yes?
Where does the cosine theta cancel out?
Where does it cancel out?
Yeah.
When you multiply it by 0.
Oh.
Yep, and it just becomes 0. Okay, we're going to try, I think I have another one of those. Yeah, but any other questions on that one first? Okay, so let's try verifying this, that the cosine of pi minus theta is the same as the negative cosine. So if this was a problem I had to do something with in calculus, I would much rather prefer to work with this because it's just an angle all by itself versus having to take pi and minusing an angle. That's a little more complicated. All right, so first thing is to figure out what identity you're going to use. So based on what's on the left, can somebody tell me the trig function and tell me the operation inside the argument? And that tells you the identity. Yeah?
Cosine difference.
Cosine difference. Yep, this is cosine difference formula. By the end of today, you'll have 6 variations. Cosine difference in sum, sine difference in sum, tangent difference in sum. One of all those. Okay, so this is cosine difference. How does cosine difference start out? Yeah?
Cosine of the first angle times cosine of the second.
Cosine, yep.
Cosine of the first angle times sine of the second.
Sine. So we got cosine plus sine. First, second. Pi, theta. All right, cosine pi. Again, that's easy to figure out on the unit circle. Focus on the x value of your coordinate. Pi, what's pi in degrees? Nick?
180.
180. So here's your coordinate. What's the x value of that coordinate? -1. So -1 times the cosine plus, now we need the sine of pi. Well, now focus on the y value of that coordinate. Yep. 0. Well, 0 times sine, this part just cancels out, so I don't even need to write it. And I'm left with -1 times cosine, which is negative cosine. And that's exactly what they wanted me to prove. Any questions on that? All right. So, we looked at the cosine difference. Now we're going to look at the cosine sum. But we're going to figure out what this one is. We're going to prove this formula based on the one we just had. So basically, everything, you can prove all of these formulas today based on the first one that I gave you. Just proving the first one, that's the one that's a little hard. All right, so a couple things are going to come up here that we've done before. We've talked about what happens when you have a negative inside the argument. Does anyone remember what you can do with a negative if it's inside the argument of a cosine function? Yep.
Can you move it to the front?
We can do that with the sine.
Okay.
With the sine, you can take a negative and move it in front. Does anyone remember what happens with that negative on a cosine function? Tim?
Isn't cosine of x just 0?
Well, we're going to have something over here with cosine.
Oh, okay.
But I'm wondering, what can we do with that negative? Well, try an example. Try taking the cosine of a negative angle, and then you do the cosine without the negative, and see the answer you get. What's the difference when you take the cosine of that angle with the negative, and then a cosine of that angle, but leave the negative off? Yeah?
Nothing happens.
Nothing. It's the same thing. So this negative has no effect on it at all. And that's because if you graph cosine, it has a certain symmetry to it. It has symmetry over the y-axis. If something is symmetrical over the y-axis, and you do a horizontal reflection over the y-axis, you're going to get exactly the same thing you started with. So there is no difference between cosine negative x and cosine positive x because of the symmetry. Now with sine, it's not quite the same thing. You can't get rid of that negative inside the argument, but what you can do is you can just move it in front. And both of these are important because in trig, we do not like to write arguments that are complicated. A negative with a letter is more complicated than just a letter. So this gives us a way to get rid of the negative. So, let's think about what this is going to be. So we're trying to figure out what the cosine of a sum is. What's the only identity that we know that we've learned today so far? Okay.
The cosine difference.
We've learned the cosine of a difference. So somehow we have to use the cosine of a difference formula to figure this out. If we can rewrite this as cosine of a difference, then it's going to start to become more familiar because we have a formula for that. How can I write cosine of alpha plus beta as a difference? Yep.
So you're saying it's the same, like the argument's the same, negative and positive. So if you just made alpha negative, and then you turned it into beta minus alpha.
Okay, so tell me what to put right here.
Beta.
Any reason why you switch the order of these?
Well, because if alpha becomes negative, right? If the whole beginning becomes negative, then you would have to make it like, what's it, plus the negative.
So what if I gave you this and I said to rewrite it like that? How would you do it? I don't understand how to do addition, but I do know how to do anything you want to do with subtraction.
Okay.
So how can I rewrite 3 plus 2 as subtraction?
You have to take the sum and then subtract what the comes from.
Maybe 3 minus -2.
3 minus -2. And I say, oh, okay, I know how to do subtraction. When I minus a minus, I just change it to a plus, and then it's equivalent. All right, so let's do the same thing here. So what would go inside my arguments? Yep.
Alpha and then negative beta.
So alpha minus beta. Now it's just a matter to figure out, well, what are your two angles here? What are the two things that you're really working with? Well, it's everything except the minus sign that's between them. So I'm going to put boxes around them, just like I did in that problem. That's my first angle. That's my second angle. Those are the two things I'm subtracting. So now, use the cosine difference formula with that as your first angle, and that as your second. Simplify it as much as you can, and that will be the formula for the cosine of a sum. All right, so, oops, delete that. All right, so how does my cosine of a difference start out? Nick?
Cosine of the first angle times cosine of the second angle.
Okay.
Plus sine of the first angle times sine of the second angle.
Second. Okay, so I've got my cosine, sine, and now fill in first, second. This time we don't have any numbers. My first angle is alpha. My second angle is negative beta. First angle alpha, negative beta. Okay, so let's look at the first term. There's two factors in the first term. Which factor there can I simplify a little bit? John?
You can just say that, cosine of negative beta is just beta.
Yep, so cosine negative beta is just cosine beta. When you put a negative inside an argument on a cosine function, it doesn't make a difference. So we can have cosine, we can do it just like that. Okay, so we've got that. Which factor can I simplify in my second term? Yep.
The sine negative beta.
I can work with that sine negative beta, and what happens to that negative inside the argument on the sine function? Yep.
It goes in front of the sign.
Yeah, it can go in front. We can't get rid of it, but what we can do is move it in front. It basically makes your term multiplied by -1. Right, so this entire term right here gets multiplied by -1. which effectively means it turns into subtraction. So minus sine alpha sine beta. And there is your cosine sum identity. So very similar to the first one. The cosines are grouped together and the sines are grouped together. But notice the pattern of whatever you have here, you put the opposite here. That pattern continues. So group your cosines, group your sines. First, second, look at the symbol you have between the two angles and make it the opposite. All right, so let's try an example. So now we could do cosine 75. You technically could have done cosine 75 without the formula for a sum. To me though, a sum comes to mind naturally with 75 versus a difference. We'll talk about a difference in a second. But let's see if we can do this as a sum. Can anybody think of two numbers that I can add together to get 75? And they have to be multiples of 30 and 45. Leah?
45 and 30.
Yep, 45 and 30. So this problem is almost identical to doing cosine of 15. The only difference is your angles aren't any different. It's just the symbol you put between them. So we've got cosine, cosine, sine, sine, and you're going to put a minus between them. 45, 30, 45, 30. Okay, and I think we've already done all of these. Does anybody remember what the cosine of 45 is? Yep. Square root of 2 over 2. How about the cosine of 30? Abel?
Square root 3 over 2.
Square root of 3 over 2. Sine of 45? Okay.
Square root 2 over 2.
Square root of 2 over 2. And the sine of 30? Yep. Good. 1/2. Okay, so that's the kind of thing, if you didn't know those numbers, you're going to spend probably 5 minutes now doing each one of those, drawing a unit circle, and it's going to take too long. If you have them all memorized like that, it's way faster. Okay, multiply it all together, and let's do a common denominator. What's my common denominator going to be for both of these fractions? Yep, it's going to be a 4. And what's going to go in the top? John?
Square root of 6 minus square root of 2.
Yep. Very easy to check it. You just type it in on a calculator. Type in cosine 75, see if you get the same thing. Now, I said that you could have done 75 instead of a sum. You can do it as a difference, and you'll get the same answer. I'm not going to go through the whole thing, but can anybody think of how you can write 75 as a difference, and it has to be two numbers that are multiples of 30 and 45? Yep.
90 minus 15.
15, I don't know, that's a tough one to remember. That's not a multiple of 30 or 45. Madison?
Could you do like negative 45 minus 30?
So that would kind of be the same thing. If you just said like 45 minus 30. Yeah, that's kind of the same thing. I'm actually thinking of different numbers where you don't have to do minus a minus. Yeah, Lindsay?
135 minus 60.
Let's see, 135 minus 60. Yeah. Yep, that would work. I was actually thinking of another one. Anybody think of another way you can get 75 by subtracting two numbers? Yeah?
20 minus 30. That doesn't make any sense. And
It is
120
120.
minus 45.
120 minus 45. So there's lots of ways to do these. Okay, you just have to come up with two numbers that add or subtract to give you the number you're looking for, and they have to be multiples of 30 and 45. Okay. Is there any question on that? All right. So we did the cosine sum, we did the cosine difference. Let's look at the sine of a sum. To figure this one out, let's graph sine and cosine. Do a zoom 7. And I just want to remember what the difference is between sine and cosine. Anyone explain to me what the difference is between those two graphs? Looking for just kind of a description, and then I want to translate that description into something that I can actually write down as an equation. Yeah?
They're shifted over 1.
Okay, they are horizontal shifts of each other. Now the question is exactly how much of a horizontal shift. The blue one was sine, and the red one was cosine. It is one tick mark on the screen, but each tick mark is not one unit. Tim?
Pi over 2.
Yes, it's a shift of pi over 2. So let's say we could write this formula two ways. Let's say we want to do sine of x equals, what would you have to do to the cosine function to turn it into the sine function? Think about the function in red. What transformation would you do to the graph in red to turn it into the graph in blue? Yep.
X minus 1.
Tell me in general first, which way would you shift the graph in red?
Right.
Okay, you'd shift it right, so we're definitely going to do a minus. That will shift it to the right.
Oh, is it pi over 2?
And the amount of the shift is pi over 2. So that's a conversion between sine and cosine. We can do it the other way too. If you took the sine function, which is the one in blue, and you shifted it left pi over 2, you could get the cosine. So what this does is it kind of gives us a bridge between sine and cosine. We have all the cosine identities we need right now. Cosine of a sum, cosine of a difference. Well, look at what's happening here. This is cosine, it's a difference. So we can use this to get a formula for sine. And that's what we're going to figure out right now. All right, so we know that sine equals cosine pi over 2. Well, I wrote it a little differently there, but it's still the same idea as what we just did there. It's the same. All right, the important thing is you understand that sine and cosine are phase shifts of each other. So now, let's see if we can figure out the sine of a sum. All right. I want to use that identity that I have up above. But basically, instead of theta, you're going to substitute that in for theta. You can substitute anything you want right here. You could put in 10, 36, or this. So I'm trying to figure out what the sine of a sum is. So let's apply this formula using alpha plus beta as my argument. Yeah.
Why is it pi over 2 minus theta in the cosine in the top right?
Why is it? Okay, I can show you real quick. Let's go back here. So cosine of pi over 2 minus theta. Okay, so that's what I wrote on the other page, right?
Yeah.
So this is a cosine difference. Do you agree with that?
Yeah.
All right, so let's write it as cosine, cosine. I'm going to do this out, and then I'll do mine out, and I'm going to show you do the same thing. That's basically what I'm going to do. So cosine, cosine, plus sine, sine. Pi over 2 theta, pi over 2 theta. Okay. The cosine of 90, that's my x value. What's the cosine of 90? 0. 0 times cosine plus, what's the sine of 90? 1 times sine. This is gone. So this thing that I wrote down on the other page is equal to sine theta. This thing that we wrote down right here is also equal to sine theta, which means that this cosine of x minus pi over 2 is exactly the same as this. It doesn't really matter which one you use, that's the point. It's just, I'm doing it the way the book did it, but does that make sense how these are really the same thing?
Yep.
Okay. Alright, so let's go back here. So now, let's fill in for our argument, alpha plus beta. So cosine, pi over 2 stays right where it is, minus, and what you put after the minus sign is your argument. Look at your argument, look at what we're plugging in, alpha plus beta. Any question on that stuff? All right, so what can we do with that minus sign? Yeah?
Well, you can move, it doesn't matter, right?
Well, we've got a lot more complicated argument there than just like a cosine minus theta. So we can't just get rid of that minus. But what can I do with it? Yeah?
Distribute.
Yeah, I can just distribute it. So let's distribute it. And let's write our answer like this. Pi over 2 minus alpha. So when I distribute the minus to the alpha, you get minus alpha. And distribute it to the beta. Now, I want to look at that a certain way. Okay, this is how I want you to focus on it. So think of that as your first angle, and think of that as your second angle. You have cosine of something minus something. So now use your cosine difference identity. This is the first angle you're going to plug in. This is the second angle you're going to plug in. Okay. So what's my formula for cosine of a difference? How does that start out? Leah?
Cosine on the argument, cosine in the argument.
So we're going to have, I'll leave enough space here, cosine, cosine. Yep. And what comes after the two cosines?
Plus sign.
Plus, you always do the opposite of whatever's between the two angles. And then what comes after it?
Sine and then sine.
Yep. Sine and sine. Now fill in your arguments. That's my first argument, which there's something we can do with that we just talked about. This is my second argument. Not much I can do with that. My first argument and my second argument. Now, look at that. Cosine pi over 2 minus alpha. What does cosine pi over 2 minus alpha turn into? John?
Did it turn into your argument for the next cosine difference formula?
So I need a trig function. What does cosine pi over 2 minus alpha simplify to? Yeah?
cosine pi over 2 plus alpha.
Sine theta.
Sine. Whenever you take cosine of pi over 2 minus an argument, it's the sine of your argument. So this entire thing turns into sine of my argument, because it's pi over 2 minus alpha. This is going to stay exactly the same. Now, this one, I didn't directly prove it. I kind of tried to explain the idea of it right here. I know my version is written a little bit different, like this one was written a little different, but what do you think? What do you think that the sine of pi over 2 minus alpha turns into? Yeah?
Negative cosine? Or just cosine?
Just cosine. Okay, whenever you take pi over 2 minus your argument, if it's a sine, it turns into cosine. If it was a cosine, it turns into a sine. Cosine alpha, sine beta. Try to keep parentheses around my argument so you can see them. And that is the formula for the sine of a sum. A little different, okay, in terms of the pattern. When you're dealing with a trig identity that has sine, it's mixed. Before we had cosine, cosine, sine, sine. I consider that to be grouped. Well, this has a sine mixed with a cosine. So it's sine, cosine, plus cosine, sine. The argument is still first, second, second. The other thing that's different, you had a plus sign between them. You put a plus sign right there. When you have a sine identity, the symbol you put between them is the same as what you started with. So similar, but there are a couple differences. So based on that, I think we should be able to write down the sign of a difference without really having to figure it out and just following the pattern. What do you think, if this is the sign of a sum, what do you think is going to change for the sign of a difference? There's only one thing that will change. Yep.
Is it the sign in the middle?
Yes. What do you think is going to happen to that?
Turn into a plus.
Turn into a what?
Minus.
A minus. Yep. It's still going to be mixed. Sine, cosine, cosine, sine. But instead of a plus between them, we have a minus.
Me too. Do you have the extra letter?
Maybe. Let's see.
Two.
Any question on that one? So now we've got the sine sum and difference. We've got the cosine sum and difference as well. Everybody have that?
Why is it a plus? Is it just not the opposite?
No, it's the same. If you have a minus inside the sine argument, you put a minus between them. It gets hard to remember once you learn them all, because then it's like, wait, do I keep it the same, or is this the one where I switch it? But this is the one where you keep it the same. All right, we don't really need to go through a whole numerical problem, but you could do something like, let's say I asked you now to do the sine of 75 degrees. How could you write, and we've already done it, how could you write 75 as a sum? Leanne?
45 plus 30.
Yeah, 45 plus 30. And then just go through your identity. You're going to get all the same answers you've gotten before. You're going to get root 3 over 2s, root 2 over 2s, 1/2s. You're going to get all those answers again. It's just they're going to be in different spots because the formula is rearranged a little bit. So any question on how you would go about finishing something like that off? Same way you do cosine of 75 and cosine of 15. Okay, so those are our sines and cosines. What if I asked you to do this? Tangent of 75. What could you technically do? You have enough information to figure this out with what I've taught you so far. Yep?
Could we do the sine sum formula divided by the cosine the sum formula?
Yes. You could just take and figure out what's the sine of 75 and go through that entire problem. Find the cosine of 75, go through that entire problem, and then just divide the two answers. Okay, so you can figure out tangents using what I already told you. Now, there is a little bit quicker way to do it, and there's a specific formula for the tangent of a sum, so you don't have to do this. Right? And I'll give you those too. And then we can try one, and I think, yeah, okay. So I'm going to give you the tangent sum and difference formulas. Again, they're not really formulas. These are ones I don't have memorized. I always have to look it up if I need to use it.
Are the sum and difference exactly the same?
No, they're, well, you could probably guess what the difference is based on looking at this one. It's just the signs change, so that the numerator becomes a minus and the denominator becomes a plus. The sine and cosine sum identities, those I can remember. But the tangent sum and difference, I usually look them up if I need them. So the tangent of a sum is tangent first plus tangent second over 1 minus the product of the two tangents. In the bottom one, it's tangent first minus tangent second over 1 plus the product of the tangents. One thing that might be handy here is to tell you a couple decimals that will come up. If you see the square root of 3, that's about 1.73. And if you see it's 0.577, this is one I started to write down at the beginning, but then I erased it. That's root 3 over 3. Because with tangent, you're dividing different sides of the triangle, you're dealing with opposite and adjacent, you can get some slightly different fractions. You're not going to get root 3 over 2s. You're not going to get root 2 over 2s when you do tangents. They just don't come up. But these do. I'm not going to spend a ton of time doing examples because really for numerical stuff, I want you to focus on the sine and cosine sum and difference. So those are the most important. Even if you never learn the tangent ones, it's really fine because you don't need them. You can do it with just sine and cosine if you had to. If we were going to be doing hundreds of problems with the tangent identities, then I'd say, yeah, these are really important. But if we only have to do 1 or 2, is it really worth trying to memorize this? Probably not. Right? So I wouldn't worry too much about these two, but if you ever need them, you have them. Okay. Any questions before we take a look at the last thing? All right, so last thing, and we're not going to finish this today, we're just going to look at the first one, is what we call a double angle. A double angle is just when you multiply an angle by 2. And the question we want to figure out is, how do you get rid of the double? It's too complicated to have a 2 inside the argument. It's going to make things very, very challenging. Well, you can't just take the 2 and put it in front. That doesn't work. First of all, think of it from transformations. This is a horizontal compression by a factor of 2. This is a vertical stretch by a factor of 2. They're just not the same thing. So let's I'm just going to say this: expand using an identity. And you should be able to figure out what the sine of 2 theta would equal. What's another way I can write 2 theta? I'll give you a hint. It's going to involve a sine identity that we learned today. What could you put inside the parentheses that would be equivalent to what I have right there? What if I just said this? What does this mean? I don't understand what 2 theta means. I've never seen a number next to a letter before. Yep.
An angle times 2, or whatever that variable is times 2.
Okay. Can you explain that to me using a simpler operation than multiplication?
2 of those thetas.
And do what with them?
Multiply them.
That would be theta squared.
Yeah. Add.
Add them. 2 theta, all that means to do is theta plus theta. Now, that's something we can figure out. This is my first angle. This is my second angle. So I'm going to do a sine sum identity where angle 1 and angle 2 are exactly the same. Okay, we haven't worked with this one a lot, so can someone remind me for the sine sum, how does it start out? Mabel?
It would be sine of theta times cosine of theta plus cosine of theta times sine of theta.
So the general pattern is sine, cosine, cosine, sine. That's your pattern. And your arguments are 1, 2, 1, 2. Theta, 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 theta. And the symbol we put here is the same as what we had there. I have sine times cosine plus another sine times cosine. So what would that simplify to? John? So it's like having x times y plus y times x. What would that really be? Yeah?
2xy.
That would be 2xy. Yeah. So what do you think this is? Nick?
2 sine times cosine.
Exactly. 2 sine times cosine. And that is what we call the double angle identity for sine. And that's the last thing I'm going to give you. Okay, the double angle identities. That's the one for sine. Sine 2 theta equals 2 sine cosine. And for cosine 2 theta, this one's a little different. You actually have choices about how you write it. Probably weren't expecting that. That looks totally different than sine 2 theta. But that is one way you can write it. And if you remember, we've kind of seen something like that before. Anyone remember what this equals? Sine squared plus cosine squared? 1. If you use this Pythagorean identity, you can rewrite this one different ways. That's one way you could rewrite it. What did they do there? They substituted for cosine squared. You can substitute a 1 minus sine squared in for a cosine squared and get that version. Or you can substitute in the other way, substitute in for sine squared and get that version. It's really 3 different versions, and which one you use in a problem, depends on the problem. If I was trying to verify something and I saw cosines in the final answer, I'd probably use the bottom one. If I saw sines in the final answer, I'd probably use the middle one. And the last one, again, the tangents, those aren't really identities that we use a lot. We're going to stick mostly with the sines and cosines. So I think tomorrow we pick up with the double angle identities, because we didn't really do any examples. So you won't really have too many examples with double angle in the homework, mostly sum and difference. All right, so on 417, let me just double check. 1 through 5, that's all numeric. 9 and 11 are proofs like we did earlier, and 17 is a double angle. That's the only double angle. We'll take a look at that tomorrow.